Hello, guys. Nice to see you.
Good afternoon.
Hi. So, how are you doing? Any plans for long weekends?
Hello, sir.
Hello.
Hi. Should
Yeah.
also
Plans.
relax, not
Good
only
afternoon.
study. Hello.
Good afternoon.
Hi.
Good afternoon.
Nice to see you. Hello. Okay, guys. How how your things are going with Long Kappa? Any problems with that? I hope not. Should be everything smooth. Okay, that's the most important part, because that will be important for your final grades later. Okay, hello everyone who just joined. So I guess people will join. It should be, there is a question like login and password to Long Kappa. It's university ID and your password to the system, I believe, to registrar should be most likely the same. Can also ask your friends, or if there are some issues with that, write a letter to our Long Kappa administrator, Azamat. Okay, so as you may remember, last discussion we introduced the motion in two-dimensional space and introduced the main parameters which we need to describe this motion, means instantaneous velocity and acceleration vectors. That's important because we already deal in two-dimensional space, and discuss some features of this two-dimensional motion in two-dimensional space on the example of projectile motion, like specific type of two-dimensional motion when we have constant acceleration, but not just constant, but also that it is oriented only through all motion. It's oriented only along axis y. There's no projection to axis x. And also based on the equations which we derived to describe this type of motion, we define the maximum height of the trajectory and so-called horizontal range, the distance between the initial point and final point of this projectile trajectory along axis x. So today we continue to work with and discuss in details motion in two-dimensional space, and all lecture we will be focused on such important form of two-dimensional motion as circular motion, mostly uniform circular motion with constant speed. However, also we'll mention a little bit about this case when we have also change of speed along circular motion. So it is important to highlight that if we have some circular motion with constant speed, it doesn't mean, so speed is constant, so automatically we would consider that there is no acceleration. However, this is not true. And any particle like body which is moving along circular trajectory will experience some acceleration, which is called centripetal acceleration. And that acceleration originates from the change of the velocity vector orientation. So it doesn't change in magnitude because speed is constant, but the change in velocity vector orientation will result in acceleration, which is called centripetal acceleration. So our goal today is to learn everything about this acceleration. Define its magnitude first with some phenomenological approach when we have some physics and geometry combined. And also later we will address analytically the exact solution, analytical solution for centripetal acceleration vector, which will show us not only the magnitude of its, but also the orientation. So we will know exactly where this centripetal acceleration vector is pointed to. Okay, so let me now change to the slide. And we can start. So let us consider some circular trajectory, segment of this trajectory, and 2 points on it. Let's call it point A and point B. So here will be the center of this circular trajectory and position vector, which defines position of point A. So we will call it R initial position. Then, of course, we need to define position vector for point B. That will be final position vector. So there will be some displacement if this particle moves from point A to B. There will be some displacement vector, and this will be delta R vector. So there is a question in the chat. So as for long kappa to accept the answer, it should be within plus minus 1% from that like exact correct answer. So if it fits into this range, plus minus 1%, which is not much, so please don't count on that, long kappa will not accept your answers. So there is some range of flexibility, but it's quite narrow. So keep that in mind. And yeah, you should get information on your answers on long kappa problems at the end of this appointment. So at the evening, Sunday evening, you should have information. Okay, let's come back to our discussion. So also we need to define velocity vector, and this will be initial velocity vector, which is always perpendicular to position vector. And here we have final velocity vector, which is also perpendicular to its corresponding position vector. So what set of conditions we need to accept at the beginning? So the amplitude of the velocity vector is constant. We consider uniform circular motion, means that the speed doesn't change. However, as you may see already here, the orientation changes. So the fact that absolute value of velocity vector is constant means that magnitudes of initial velocity is equal to magnitude of final velocity. So we can write it that it's equal to some this magnitude of the linear velocity, which is constant. So orientation is different. So next step for velocity vectors. Next step, what we do, let us move these vectors, initial and final velocity, put their origins in the same point, and draw it just underneath. So here will be our initial velocity vector. Here will be our final velocity vector. So now let us consider that there is some angle between initial and final position vectors, which is theta. If there is some angle between initial and final position vector, theta, taking into account that velocity vectors are always perpendicular to their corresponding position vectors, then we can also write that angle between these two velocity vectors will be theta. So since we have the same angle for these two triangulars, let's call it position vector and velocity vector triangulars, means that these triangulars are similar. So actually, in order to have this complete triangular down in the down part of our figure, let's do the following. We can represent final velocity vector as the sum of initial velocity vector plus delta v, like change of the velocity vector. This delta v will be here. So now we have these two triangulars, r initial, r final, delta r, v initial, v final, delta v. So these two triangulars are similar because we have the same angle here. For similar triangulars, the ratio of two sides of a triangular is constant. So it's equal to each other. So we can write, for instance, that delta v, we take into account lengths of vectors, so their magnitudes. Delta v divided by v, because here it doesn't matter it's vi or v final, they are the same in magnitude, could be written as equal as delta r divided by r. So again, we have r instead of ri and rf because they are the same since it's circular trajectory and radius of the circle doesn't change. So it's in magnitude, it's constant. Only orientation of these vectors is changing. So now let us express delta v from this equation. It will be v times, let's say, maybe better in a different form, will be v divided by r times delta r. Now we remember from previous discussions, let us introduce this average acceleration. This is equal to delta v over delta t. So since this is uniform circular motion and speed doesn't change, the magnitude doesn't change, so of velocity vector, it doesn't change over time, it's kind of steady state condition. And that's why our average acceleration will be also our instantaneous acceleration. So let us now substitute delta V here with its expression. So let's call this average acceleration is equal to V over R times delta R divided by delta T. Okay, so now if we consider some case when we put points A and points B very close to each other, that will automatically mean that the time interval which takes to travel from point A to point B, which is delta T is equal to T final minus T initial, will approach 0. So delta T will approach 0. And what is also very important, when we put these points A and B very close to each other, then delta R, the displacement vector, by its magnitude will approach to the path between points A and B, means the length of the trajectory it actually travels through. So now at this figure, we see that when points A and B are quite far from each other, that this magnitude of displacement vector is definitely smaller than the path. However, when we put closer and closer this, when point B, for instance, approaches point A, this difference will become negligible, and magnitude of delta R will be actually the path between point A and B. So taking this into account, we can write that this ratio is nothing else as magnitude of our linear velocity. And here we will get V squared divided by R, and this will be our centripetal acceleration. So with this combination of physical considerations and simple geometry, we could derive expression for the magnitude of centripetal acceleration, which is proportional to magnitude of linear velocity vector in second power divided by radius. So that is good. However, that's not enough, because we know that this centripetal acceleration is also a vector, and we need to define the orientation of this vector. However, at this point, we cannot tell much about orientation. There could be some assumption that if we move point B towards point A, then the angle theta will be will approach 0, means that the angle between VI and VF also will approach 0, and the angle between delta V and VI, for instance, will approach 90 degrees. Means that if this is direction delta V, which defines this centripetal acceleration, is perpendicular to the linear velocity vector, radius vector, like position vector, is also perpendicular to the linear velocity vector. Means they have the same alignment. However, we cannot say anything about the exact orientation. Means is it pointed towards the center of this curvature in opposite direction to the position vector, or outside from the center, means in the same direction as position vector. So that is not clear, and in order to answer that question, we will need to add more some like analytical solution for this particular case. However, before that, we need to discuss few things. So first of all, very shortly, let us mention about the option when we will not have uniform circular motion, but let's say amplitude of the linear velocity vector will not stay constant. So in this case, we will also have centripetal acceleration, obviously, because velocity vector will change its orientation while particle is moving along circular trajectory. However, in addition, we will have so-called tangential acceleration, which is equal to the derivative of this velocity vector over time. And that obviously originates from the change of the magnitude of this velocity vector. So that's why, for instance, we have some circular trajectory. Here we have this particle. This is velocity vector orientation. Here will be the same direction, tangential acceleration vector. And here will be this, when we have both tangential, and we also call this radial acceleration, then it automatically defines the orientation of these accelerations along velocity vector or along the position vector. And the total acceleration obviously will be defined by the sum of two vectors of tangential and radial acceleration. So we will get for the magnitude of total acceleration a tau square plus a r square. Okay, so this is very shortly about the case when we don't have uniform circular motion. However, let us come back to uniform because we need to define some angular parameters which are very convenient to describe uniform circular motion. So we can write that amplitude, like magnitude of the linear velocity vector, is equal to 2 pi times r divided by capital T. So here in the numerator, 2 pi times r is just length of the circle. And in the denominator, we have this capital T, which is the period. So period is defined as the time which a particle needs to take in order to make a full circle, like full rotation along circular trajectory. So full rotation means 2 pi radians, or this is equal to 360 degrees. So now we can consider this part and substitute it with some parameter omega. So we can write V is equal to omega times R. So this omega is angular velocity, means how many radians per second this particle is moving along circular trajectory. So we also can define, obviously, angular acceleration. Sorry, not angular acceleration. That will be in future. We obviously can define centripetal acceleration in terms of angular velocity. So centripetal acceleration, we know it's v squared divided by r. So instead of v, we can substitute omega r. So we will get omega square r square divided by r. And here we cancel out this second power and radius in the denominator. We end up with omega square times r. So these are important things to know. Please remember these equations for centripetal acceleration in terms of linear velocity and angular velocity, because they will be used very often. So now we can, after introducing these concepts, like angular parameters for quantifying circular motion, we can proceed further with this analytical solution, which will give us the exact analytical derivation of the centripetal acceleration vector. So we will know both magnitude and orientation. Let's go here. For this purpose, let us consider circular motion in such system of coordinates x, y. This is the circle. The particle is moving along. Here's our particle. Here is position vector, which we yeah, let's call it position vector. We can also call it like radius vector. It doesn't change in magnitude. It only changes its orientation. But let's call it position vector, more general. And here we have theta, like some angle between this position vector and axis x, which actually with the magnitude of this position vector and this angle, we can, in polar system of coordinates, define position of this particle. So we assume that we have uniform angular motion, which is absolute value of linear velocity vector is constant, and actually even show it here. Linear velocity vector. Also, if linear velocity is constant, and we know that linear velocity can be expressed as omega times r, means that angular velocity omega is also constant, because r, radius, is constant by definition. It's a circle, it doesn't change. So maybe also would be good to recall that centripetal acceleration, its amplitude, is equal to omega squared times r. For later. So now what we need to define the this position vector r in a vector form in the perpendicular system of coordinates x and y. So let us split it in two components as we described things earlier. So we know that in order to do some quantitative analysis of vectors, the best way is to split them in two components which are aligned along axis of coordinates. So here will be radius, like projection of radius position vector Rx. Here will be Ry. And magnitudes of this Rx and Ry can be easily defined because we know this angle theta and amplitude, like magnitude of the position vector r. So Rx will be equal to r times cosinus theta, and Ry is equal to r times sinus theta. Okay, So this is given. And now let us write down the expression for position vector in two components along axis x and y. So r vector is equal to rx vector times unit vector I plus ry times unit vector j. And this will be, or maybe we can take radius out from parentheses. So this will be unit vector I times cosinus theta plus unit vector j times sinus theta. Okay, so this is the expression in vector form for position vector. But what is special about this expression, that it gives us position vector at some random but given moment of, like one moment of time, because we have exact orientation of this radius theta at some moment of time. It can be any moment of time, but only in this one moment of time. And that's all. And that is not what we actually need, because we want to have radius expression for radius vector as a function of time. So you remember that the main goal of kinematics is to have this function r position vector as a function of time. Now, based on this expression and our conditions, any ideas how we can go from this time independent expression to time dependent?
Maybe replace r by velocity or acceleration.
R we cannot replace because this is a constant. This is the radius of our circle, and we don't change the radius of our circle. It's constant by the condition. We have circular motion, means r doesn't change. Only orientation of r changes. And that is where we need to look more carefully.
We should change the angle theta to omega t.
Oh, that is correct. We know that we have angular velocity, omega. Its units of angular velocity is radian per second. So if we have omega times t, means we have radian per second times seconds. And seconds will cancel out, we will get radians. So we will get actually the angle. But that is way more important for us to use omega t instead of theta, because we have already time dependence. Moreover, we mentioned this already, that since our the magnitude of linear velocity doesn't change, our angular velocity is also constant. So it makes our lives easier, because we don't need to consider omega also as a function of time in addition. It's just constant, and that's all. So it's not function of time in this case. So let us introduce, instead of theta, this omega t. So it will be r times I unit vector cosinus omega t plus j unit vector times sinus omega t. Okay, so now we have what we want. We have position vector as a function of time. So we know also that by knowing this position vector as a function of time, we can easily get acceleration vector. So acceleration vector, and this is what we would like to eventually have for this case. Since it's uniform circular motion, velocity, a magnitude of velocity is constant. We don't have tangential acceleration component, and our total acceleration vector will be defined only by centripetal acceleration vector. So acceleration vector will be is equal by definition which we provided last discussion to the first derivative of velocity vector over time, and we can write it as second derivative of position vector over time. So now what does it mean? We need, in order to go from our position vector as a function of time, take the second derivative over time, and we will get our expression, analytical expression for the centripetal acceleration vector. And that is important, vector, not just magnitude, which we did 10 minutes ago. But this will give us both magnitude and orientation. So let us do it. So maybe we can rewrite on next slide this equation. So we have it in front of us. And then we will go with two derivatives. So let's write here position vector as a function of time is equal to r times I unit vector times cosinus omega t plus sinus, sorry, I forgot this j unit vector times sinus omega t. Now, what we need to remember before we proceed with this differentiation, that derivative of cosinus x is equal to minus sinus x, and derivative of sinus x is equal to cosinus x. So these are common derivatives from this table of derivatives. Better remember this, or just keep table of derivatives and integrals close to you, because you will need it quite often during your study. So keeping this in mind, and also another factor which should be kept in mind. So here we have not just cosinus t, but we have cosinus omega t, and omega t is considered as a function itself. So the argument of cosinus and argument of sinus is a function itself. So we need to, in order to take derivative of such function, we need first take derivative of cosinus with its argument omega t, and then multiply it by the derivative of the argument, which will be just omega, just constant. Okay, so now we can take the first derivative of position vector dt. And this will be r constant we can keep here out of parentheses. Then we have I unit vector times omega, is that which we get from the derivative of the argument, times minus sinus omega t. So let's put this minus here, will be cos times sinus omega t, and will be plus j unit vector, again omega, times cosinus omega t. Okay, so this is done. But now we need to, so this is actually our velocity vector. But we are interested in acceleration vector. And that is, so acceleration vector is equal to the second derivative of r vector over dt squared. So now we take derivative already from this expression over time. We keep r again outside. Here will be minus I unit vector. It will be already omega squared because we will multiply once more by omega. Omega squared times cosinus omega t. And here will be already minus because we have cosinus, so it will be derivative will be minus sinus omega t. It will be minus j unit vector times omega squared times cosinus omega t.
No, that should be sine.
Sorry, yes, you're right. It would be sinus. Sinus omega t. Exactly. So what we can do with this? Let us take out of parentheses minus omega squared. So we have omega square here, and minus everywhere. So minus omega squared times r, and in the parentheses we will have I unit vector times cosinus omega t plus j unit vector times sinus omega t. Okay. What do you see here in this equation? There's some similarity with previous equations which we defined. If you take a close look to this final equation, you will see that this part is nothing else as this part. Means that this is just our position vector. So now we can finally write that acceleration, which is centripetal acceleration when we have uniform circular motion, is equal to minus omega squared times r vector, position vector. So this is centripetal acceleration vector. So now we can write it here. We already have shown previously that magnitude of centripetal acceleration is v squared over r, or it's equal to omega squared times r. So this is true because if we take absolute value of this expression, this will be omega squared r. So our derivation based on these physical concepts and geometry gave us correct expression for the magnitude. However, this analytical derivation is way more useful because it clearly defines the orientation of centripetal acceleration vector. So we know that if we have some circular trajectory, and here is the center. So position vector is oriented from the center towards the position of the point or the body which moves along this trajectory. So this is our position vector. But here we have minus. So it tells us that it's oriented in the same, like in parallel to the position vector, but its centripetal acceleration is pointed down to the center of the trajectory. This is our centripetal acceleration vector. In opposite direction, here we have this minus, to the position vector. And that is already a big deal because we know finally both magnitude and orientation of this centripetal acceleration, which originates from the change of the position of velocity vector, not change of its magnitude over time during circular motion. So this is everything what I wanted to tell you today. If you have any questions, you are welcome. So in the meantime, I will just recall what we discussed today. We introduced the, I continued to discuss topic of motion in two-dimensional space. And today, in particular, we made it on the example of circular motion, a uniform circular motion when magnitude of velocity vector is constant. Derived expression for phenomenologically for acceleration, magnitude of centripetal acceleration, which originates from the change of the orientation of velocity vector. Also, we mentioned that it's possible that we don't have uniform circular motion and there will be some change in the magnitude also, and change in the magnitude of linear velocity will result in so-called tangential acceleration, which is aligned in the same direction as the velocity vector. So they eventually we will have both centripetal acceleration, which is considered in that case as radial acceleration, and tangential acceleration, and they will define as a vector sum the total acceleration of the particle. And what is important with our first derivation, we could not define the orientation of this centripetal acceleration vector, but based on the analytical derivation of taking second derivative of position vector as a function of time over time, we could clearly show the analytical expression for centripetal acceleration vector, and that tells us both magnitude, which is omega squared times radius, and also orientation. With this minus in front of the equation, it tells us that centripetal acceleration is always oriented in the opposite direction to the position vector. Means it's pointed from the particle which moves along circular trajectory towards the center of the circular trajectory. So these are our main things to take home and remember from our discussion. If you have any questions, you're welcome. If not, I would like to wish you a good long weekends. On Monday, this is holiday, we will not have our online lecture. So hope to see you relaxed and cool with energy on Wednesday on our discussion, and take care and have a good day.
Thank you, sir.
Thank you very much.
Thank you. Goodbye.
Yeah.
Thank
you.
you.
Goodbye.
Goodbye.
Bye.
Goodbye. Have a great
Bye-bye.